from my classroom, I decided I'm going to just make this video now. I'm going to go through a series of examples, and we're going to talk about using the convergence tests. So the first example that I'm going to look at is this example right here. So I write this down. The first test I always look at is the nth term test. Your book calls it the test for divergence. It says look at the limit of the nth term. If it's not 0, it diverges. If it's 0, you don't know. It could still converge, it could still diverge. Well, this limit is 0 of this term right here. But then I noticed this is a positive series. What's that mean? Every term of the sequence is positive, so I'm just adding positive numbers together. So for large N, the numerator is looking like that, and your denominator, I'm not going to worry about the doubling, I'm just going to say, I'm going to leave it as 1. So this, as a term, looks like that. So I'm going to use a comparison test. I'm going to compare it to the series 1 over n, where n goes from 1 to infinity, which is a divergent harmonic series. Now, the next choice I have to make is which comparison test. The limit comparison test is far more forgiving, so that's what we're going to use. So we're going to form the ratio, and I say, well, I'm going to take a sub n. When I divide it by 1 over n, that's like multiplying by its reciprocal. Now I have a rational expression where the degrees are the same, so I know this limit is going to be 1/2, but I have to go through this. The limit as n goes to infinity of the ratio. We want to be good in mathematics, which is the limit as n goes to infinity of what we did here, which is 1/2. Now, 1/2 is finite, 1/2 is positive. Therefore, by the limit comparison test, the series n equals 1 to infinity of n over 2n squared plus 1 diverges. Now here's what's really happening. The reason we have this limit that's a half in this case is because these two series that I'm using are growing at the same comparative growth rate, and that's why I have a finite limit. Now, the next example that I would like to look at is this example. As soon as I see a power, I say, hey, could this be a geometric series? Or could it be a ratio test? Or root test? Now look at this and I'm like, hey, the simplest form, this is an infinite geometric series. The easiest way is the geometric series test. So I look at the absolute value of the common ratio. I don't even care what the first term is, and I realize that that's a proper fraction. Therefore, it converges by the infinite geometric series test. It converges. And you'd say it, they don't like it, you need to be specific and write this out. And I apologize. Converges as the absolute value of r is less than 1. And make sure your as looks like an as, unlike mine, which is like an r. Okay. Let's see. Now, let's look at another series. Now, you should be hitting pause and working through these with me. All right. So I look at this series, and I'm going to use the ratio test. Now I'm going to use the one for absolute convergence. So I need to form a sub n plus 1. And when I form this, I'm going to rewrite this because I know ultimately I'm going to simplify this out. And then this way, n plus 1 factorial is n plus 1 times n factorial. So now the absolute value of the nth plus first to the nth term. So get ready to do some plagiarizing. Now remember, when you divide by a sub n, you multiply by the reciprocal here. And in this case, that's n factorial over minus 1 to the n times 2 to the n. 2 to the n simplify out. The minus 1s to the n simplify out. The n factorial simplify out. Then we have the absolute value of negative 2. The absolute value of a positive integer is the positive integer. So this is 2 over n plus 1. Now I take the limit, and I like to call this rho. Now, as I've told you, right now I don't need it, but I'm going to keep doing that. Because when I get the power series, I like to use this to make my life easier. So the limit as n goes to infinity of the ratio of the nth plus first to the nth term is the limit as n goes to infinity of 2 over n plus 1, which is 0. And 0 is less than 1. Therefore, by the ratio test, the series minus 1 to the n, 2 to the n over n factorial converges absolutely. Now, this is where you have to be careful with theorem work. Since it converges absolutely, that means the series converges. Oh, that was 0, not 1. I copied it wrong. But now notice that extra work we had to do. And now, then there's another series test that we looked at. It was the cousin of the ratio test, and it's called the root test. I want to give you an example of a root test. Since everything is to the nth power, I'm going to use the root test. So I'm going to take the absolute value of the nth term, and I'm going to take its nth root. Well, this is all positive numbers, so this is n to the n plus 1 to the n to the 1 over n is n over 2n plus 1. So the limit, and let me put rho there, as n goes to infinity of the nth root of the absolute value of the nth term is the limit as n tends to infinity of this nice rational fraction. The degrees are the same, so it's the ratio of the leading coefficients, which is 1/2. That's finite. When I compare it to 1, it's less than 1. Therefore, by the root test, the series n equals 1 to infinity of n over 2n plus 1 to the n converges absolutely. Which means it converges. Oh, if I write down the series, don't do what Mr. Isaac did. Okay, so I've already done some examples, root, ratio. Oh, but let's talk about this for a second. They say the root test is optional. That whenever you use the root test, you can use the ratio test, and that is correct. Unfortunately, usually the algebra is a lot messier when you're using the ratio test, so I'd recommend knowing the root test just to make your lives livable. Now, let me go find another one. Yeah, I'm looking through here for a variety of examples just so that my young adults can okay. Okay, I'm going to hit pause. And I'm sorry about that. The motion sensor turned off. Now this one is an interesting one, because the first thing I'm going to do is rewrite the denominator. And I used to think this when I was very young, but it's not a p-series. That's a multiple of a p-series. So I'm going to factor the 4 out. And there's just a little bit more work. Now I have a p-series. I look at its power. So it's 3 halves, so it's convergent. So it's convergent p-series because p is 3 halves, which exceeds 1. Now, this is a scalar multiple of a convergent series, and therefore it's convergent. So 4 times 1 over n to the 3 halves, n equals 1 to infinity, is a scalar multiple of a convergent series and is convergent. That's a theorem. But notice we had to do a little bit more work. Okay. Now let's take a look at this one. N equals 1 to infinity. And as soon as I see this one, okay, oh no, 3. I'll factor the 10/3 out. I'm going to rewrite this as a power. Okay. Now, like before, that's a p-series. So the first thing I'm going to talk about is that p-series. Then let's look at one that's divergent. Is a convergent p-series because p is 3 halves, which is bigger than 1. So 10/3 times this series. Okay, now remember, this is a finite number. So a finite number, this series is convergent. So this sum is a finite number. Is the scalar multiple of a convergent p-series, doesn't even matter, just a convergent series, and is convergent. Now, I wanted to look at one. Let's say I gave you something like this instead. K equals 6 to infinity of 1,000 over k to the 2/5. Factor out 1,000. Now it's a p-series. This is a divergent p-series because its power is 2/5, which is less than 1 but bigger than 0. So is a divergent p-series because p is 2/5. Now, you want to make sure you say it's bigger than 0. Now, here's why. Because if this was like negative 6/5 or any kind of negative number, the limit of that term would not be 0 and it would diverge by the nth term test. So it's just really subtle. Now, you have to be careful. If I take a divergent series, if I multiply it by 0, it converges because I'm adding infinitely many zeros. So I look at this number, it's a scalar multiple and it's non-zero. A scalar non-zero multiple of a divergent series is divergent. Therefore, the series from 6 to infinity of 1,000 over k to the 2/5 diverges. Okay. Now, so here's a series of positive terms. First of all, it's not positive. After the first term, it's positive. Because the first term is 0 over 1 squared, which is 0. Second term is ln 2 over 4, and so on and so forth. And if you think about this, if you think about the functions y equals x squared and y equals ln x, they both grow without bounds. So the limit at infinity is infinity over infinity. However, y equals x squared dominates the natural log of x. So this is growing faster than this. This should have a limit of 0. So let's try the ratio test. So the n plus first term the absolute value of the ratio of the nth plus first to the nth term is the natural log of n plus 1 over n plus 1 squared times n squared over ln n. Now, I'm going to gather like things. N squared over the quantity n plus 1 squared is n over n plus 1 quantity squared times the natural log of n plus 1 over the natural log of n. Now, if you think about this, the limit of just this piece, as the quadratic is a composition and the inner side function's a rational expression, the outside function's a square. The square function's continuous for all reals. So the limit of this is the same thing as the limit of the inside squared. That's 1 squared, which is 1. This is the one we need some help with. So we have an aside. So I'm going to let f of x be the natural log of x plus 1 over the natural log of x. Okay, it's a function model for just that piece. I'm doing this so I can take its limit and I can use the theorem of L'Hopital. So the limit as x goes to infinity of f of x is equal to the limit as x goes to infinity of the ratio of this to this. Now, the limit of the numerator is growth without bound, infinity. The limit of the denominator is growth without bound. Both the numerator and the denominator are differential functions for all positives. The theorem of L'Hopital applies. The limit as x goes to infinity of 1 over x plus 1 divided by 1 over x. Well, that is the limit as x goes to infinity of x over x plus 1. And you have infinity over infinity. And again, both functions are differentiable for all positives. So this is the limit as x goes to infinity of 1 over 1, which is 1. Hence, the limit as n goes to infinity of the natural log of n plus 1 to the natural log of n is 1. Why their relative growth rates are identical. Now let's put Humpty Dumpty back together again. I think we're about to have this test fail. That's good. And go back up and look at what you had. And we have a limit of a product, which is the product of the limits. And that's 1 times 1, which is 1, which equals 1. Therefore, the test fails. You got to compare it to something. So now we have to do another test. Well, let's go back and take a look at this. I gotta think about that. What test would I use there? All right, so we've got some interesting things to think about. So if we think about the natural log of x, does it look kind of something like this? And there's a function that's a nice power function, right? That they get close to each other as it grows without bound. So we have ln of n over n squared. So this should be close for large n to the square root of n over n squared, which is 1 over n cubed, n to the 3 halves. So that's a convergent p-series. Okay, so hold on. So let's see how I'm going to explain this. Because I know that what I'm going to do, I know that this is less than this, and this is positive, so I don't use direct comparison. But I got to think about how I'm going to prove that, so hold on. Okay, the natural log of n is less than the square root of n, and this is positive. Okay, now I'm going to divide everything by n squared. So I now have that 0 is less than ln n over n squared, which is less than 1 over n to the 3 halves. So we're going to use direct comparison test. I'm going to compare it to 1 over n to the 3 halves. N is 1 to infinity, a convergent p-series, because p is 3 halves, which is bigger than 1. Oops. Okay, now let's think about this. So we know that 0 is less than the summation of the natural log of n over n squared, where n goes from 1 to infinity, but that's less than the summation from n equals 1 to infinity, 1 over 3 halves. So, by the direct comparison test, the series ln n over n squared, where n goes from 1 to infinity, converges. Okay, that was a lot of work to do. I hope you found this helpful. And I'm glad we did that last problem because I thought the ratio test was going to work there, and it didn't. We had to go to a second test, and that's good. It's good for all of us. I should see people in for help tomorrow. Bye.